Okay, the question with us is that there are three sets X, Y, and Z such that X union Y equals to X union Z and X intersection Y is equal to X intersection Z. So what do we have? What is given to us is that X union Y equals to X union Z and X intersection Y equals to X intersection Z. What we need to prove is that Y equals Z. Okay, Y equals to Z. So how do we proceed? Let's start with what is given to us. X union Y equals to X union Z is given to us. Okay, if I take intersection with Z on both the sides, it will still remain equated. So let's do that. So X union Y intersection Z will equal to X union Z intersection Z. Okay, now X union Y is now this part X union Y intersection Z. Now this equals to X intersection Z union Y intersection Z. Okay, so we have, this implies X intersection Z union Y intersection Z equals to, now this part, this actually equals to X union Z intersection Z actually equals to Z itself, Y. Just see, if this is Y, this is this is X, this is Z. Okay, so the union is complete this portion, right? Both Z and Y involved in it. Now when you take intersection of this with Z, the only thing that would remain is Z itself. So that's why this actually equals to Z itself. So here you have Z. Okay, now this implies, what is X intersection Z? X intersection Z is actually equal to X intersection Y, and here you have Y intersection Z, right? Now that means this is the distributed manner of writing it. We can write it as X union Z intersection with Y. Okay, intersection with Y. This is because X intersection Y equals to X intersection Z, right? So this is because of that reason. Now this is equivalent to this. Now because again X union Z actually equals to Y union Z. Okay, so you can write this as Y union Z. Y union Z intersection Y intersection Y. Now just similar to the reasoning before, we gave Y union Z intersection Y will actually equal to Y. Why? Because see, again, if this is Y, this is Z. Now, so the union contains complete this, but if you take intersection with Y, the only part that remains is Y. So this implies Y equals to Z. Okay, and we have proved what we wanted to. Okay, in the question we're given that there is a committee. 50 people out of that committee speak English and 20 speak French. Okay, 20 speak French, and 10 can speak both the languages. Now we need to find out how many people speak at least one of these language. So what is given to us? Let me just write down what is given to us. Given to us is that, first of all, let's denote E as the symbol for the set of people who speak English, and F, set of people who speak French. Okay, so what is given to us? We are given that number of people who speak English is 50, number of people who speak French is 20, and number of people who can speak both, that is the intersection, is 10. What do we need to find out? We need to find how many people speak at least one of the two languages. That means how many people are actually there. That's what we have to find out. We need to find out how many people can at least speak at least one of these languages. So we need to find out what is E union F. Okay. Now by cardinal property, sets have a cardinal property. So by that, you know that N E union F equals to N E plus N F minus N E intersection F. Okay, so that equals 250 plus 20 minus 10, which equals to 70 minus 10, that equals to 60. So the total number of people in the committee, 60 can speak at least one of these languages, right?